All right. Hello, AP Calculus students. Welcome to our next version of This Week in AP Calculus. So my name is Mr. Rich, and I am going to show you a couple of things that we learned this week in our class, and maybe something that we're about to learn this coming week, which is the limit definition of a derivative. So we've been through the first unit where we looked at how to work with limits of functions and what do they represent, and how do they help us characterize what's going on at a particular point, around a particular point on a function. So we have been really doing that for about 3 weeks now. But now what we're doing in Unit 2 is we're going to actually look at how we use limits to define what we call the derivative of a function. And what derivatives are going to allow us to do is find slopes of tangent lines to functions at particular x values. So what I'm going to do tonight is I'm going to show you develop the formula that we use that we call the limit definition of a derivative. And then I'm going to use that on a few example problems on how to find a derivative and then how to find an equation of a tangent line at a particular point on a function. So I'm going to share my screen and we'll get right to it. So let me bring up the big screen here. And I think that is what we want right there. All right, so here's where we are going to start. So I've got here just some random function f of x. And if you are watching live, leave me a comment. Let me know that you're here, or if you have any questions, feel free to put those into the chat. But here is a random function f of x, and this line that I have drawn that passes between these 2 points, right? This curved line is the f of x function, and I've drawn what we call a secant line that passes through 2 points on that function f of x. And so what I want to do is write an equation of that, or an equation for the slope of that secant line. Now, notice that I have defined one of the values of x to be x right here. And then I've decided to come out a distance h away from x, which would make then this value on the x-axis x plus h. That also would mean that this associated y value, we can call that f of x, and the y value that goes with the x plus h, we're going to call that f of x plus h. Now, the slope equation is pretty simple, right? You've known the slope equation ever since you were probably in 7th or 8th grade. And the slope of a line in the xy plane is written as y2 minus y1 over x2 minus x1. So if I know 2 points on a function, I can get the slope of the secant line just by using that equation. But now what we are going to do here is we're going to say that that slope of that line is, instead of y2, I'm going to call it f of x plus h, because that is the y value here, minus the other y value, which would be f of x. And then my x2 would be x plus h minus the x1, which would be x. Okay, now what that means is I could simplify this. The slope of that secant line is going to be f of x plus h. That's my difference between my two y values. And this simplifies to just h, because x and negative x will knock each other out. So there I go. So that is the slope of that line. But here is what we want to do. If I don't want a slope of a secant line, but I want a slope of a tangent line at x, then what I would need to do is really move this other point along the curve to get it closer and closer. Right? If I moved it to right here, my h would have shrunk. Right? It'd be a smaller h. My secant line would now look something like that, okay? But I don't want to stop it there. That wouldn't make any sense. If I move that point and move it and let it get infinitely close to this point. Now, I can't let it get all the way there. I can't let it get all the way to that point, because then I would have 0 over 0, right? F of x plus h minus f of x. If these 2 points, if I move this point on top of that point, then there is no y value. And there would be no x value. So it would be, in a sense, 0 over 0, which doesn't mean that the slope doesn't exist. It just means we don't know what it is. So I'm actually not going to let that point. I'm not going to let this point get all the way to it, but I'm going to let it get infinitely close to it. All right. So I'm going to let it get as close as I possibly can. You say, well, how close is that? Well, it would be x plus 0.000, an infinite number of zeros, and then maybe a 1. So I'm going to get it as close as I possibly can, and that's where limits come in. Because the closer that this point moves and gets closer to that point, then that h is going to approach 0. So what I'm going to do is simply write a limit, right? I'm going to let the limit as h go to 0 of this slope expression that I have. I'm going to write it like this, okay? And so that is the slope of the tangent line at x, okay? Because if h goes to 0, then those 2 points are on top of each other. That's no longer a secant line. By definition, that's what's called a tangent line, right? When you have a line, right, that would nick a curve at one point. You learned this in geometry as the tangent of a circle, but we have tangent lines to any curved function. If that line touches it at just that one point, then that's called a tangent line. So my secant line turns into a tangent line as h approaches 0 in my diagram. And so this thing right here is what we call f prime of x, or we call it the derivative function, or just the derivative of f of x. It's what we call the limit definition of a derivative. So in other words, if I take this limit right here as h goes to 0 for any function x, and I apply this limit, I'm going to get a new function that will give me the slopes of the tangent lines on that function for any value of x. That's what we call the derivative. So this really, you could think of this f prime of x as the slope function, right? F of x gives me y values for my function. You give it an x, it'll spit out the y coordinate for that function. But if I take an x value and put it into its derivative function, it's going to return to me the slope of the tangent line of f of x at that particular x value. Now, I'm going to work an example here. Hopefully, I got enough time tonight to show you an example of this, and we'll actually graph the tangent line, and maybe it'll make a little bit more sense. But for now, what we want to do is we want to take this definition of a derivative and apply it to an actual function and look and see how that algebra and that analysis would work out. So I'm going to go down here and I'm going to work this problem here. This says to use the limit process of the derivative to find the general formula dy dx for the derivative of f of x equals 2x squared minus 3x. Now, notice this notation here, dy dx. That's another way that you will see eventually in your class that we express f prime of x, the derivative function. Okay, so I'm going to refer to this as f prime of x. So here's what I want to do. I'm going to find f prime of x for this function f of x by subjecting it to this limit. The limit as h goes to 0 of f of x plus h minus f of x all over h. And so how do we do that? Well, we're just going to do it, right? You've probably done one of these, what we call a difference quotient in your pre-calculus class, but I'm just going to do what it says. So what I'm going to do is take f of x plus h, which means I go to the f of x function and replace both of those x's with x plus h. And so this right here that I've just written, that is my f of x plus h. Then there's a minus sign. And then in parentheses, very important that I put this in parentheses, right? Anytime I do a substitution, I put the quantity, whether it's a number or an algebra expression, putting it in parentheses. So this becomes 2x squared minus 3x, and that's all over h. Now, it's important to understand that as you were learning about limits, your teacher told you that the very first thing that you do when you're trying to evaluate a limit is you try to evaluate it using direct substitution. So you may be saying, Rich, why didn't you try direct substitution? Well, I kind of know what happens, right? If I do that. If I try direct substitution right here, I get 0 over 0 because it would be f of x, right? As h goes to 0, not x. As h goes to 0, this would be f of x minus f of x, which is 0, over h going to 0. That would be a 0. It would be 0 over 0. So that means I have more work to do. It doesn't mean that that this limit doesn't exist. It just means we don't know what it is when I get a 0 over 0. All right, so we continue on. Now, even here in direct substitution, if you put zeros in here for h, it's still 0 over 0. So our strategy in this particular case is I am going to expand everything in the numerator, combine like terms, and then try to simplify. So here we go. So I'll square that binomial. So that's going to be 2 times x squared plus 2xh plus h squared. I'll distribute that -3. That'd be a -3x minus 3h. I'll distribute this minus. That's going to give me a -2x squared and then a positive 3x. Now, I am going to do one more algebra step here because I need to distribute that 2 that's out in front of those parentheses. So this will become my whole entire big numerator is going to be 2x squared plus 4xh plus 2h squared minus 3x minus 3h minus 2x squared and then plus 3x. And that again is all over h. Now what happens here is there's going to be quite a bit of cancellation going on. So you can see that this 2x squared and -2x squared cancel. I have a -3x and a positive 3x. What I'm left with are 3 terms in the numerator. So I am going to write this down. And this is not x, this is h, as h goes to 0. Okay, we're letting h go to 0. Again, why are we letting h go to 0? Again, it goes back to this picture that we started with. If I want to move from a secant line to a tangent line, I need h to go to 0. Okay, so that's what we're doing here. And this leaves me 4xh plus 2h squared minus 3h. They all have a common factor of h, which I am going to factor out. And it looks like that. Okay, so I took these 3 terms that all have an h and factored out the h as a common factor, which means then that those h's cancel. Now I can use direct substitution. Right? Before this moment, all of my other expressions would have yielded 0 over 0. But now since those h's cancel and I let h go to 0, I get an answer of 4x minus 3. So what does that mean? That means f prime of x is equal to 4x minus 3. Now, to make sense of what f prime of x means, I have to know what f of x is. So I'm going to rewrite what my f of x function is down here. So this f of x function that we started with was 2x squared minus 3x. So these two are related to one another, right? Because the f prime of x is the derivative of f of x. So this gives me y values, this function right here. For example, if I'm interested in the location x equals 2, f of 2 would be 2 times 2 squared minus 3 times 2. 2 squared is 4, 4 times 2 is 8, 8 minus 6, it's 2. What does that mean? That means that the point 2 comma 2 is on the function f of x. But what if I find f prime of 2? If I calculate f prime of 2, that's 4 times 2 minus 3. That's 8 minus 3, that's 5. Well, what does the 5 represent? Remember, the derivative function is a slope function. It's returning values of slope. So this means that at this point, 2, 2, the slope of the tangent line is 5. That's what that means. And I'm going to show you that graphically here. So let me fix this so I can show you. And I'm going to set this up in Desmos, right? So as you know, I'm a big proponent of using Desmos when you're trying to learn what these functions look like. So what I want to do is I want to graph this 2x squared minus 3x. That was our function. And our derivative of that function is y equals 4x minus 3. And that's my dog deciding to bark. Okay, turn that off. All right, so let me share. I'm going to share this back with you. Okay. Let's see if I can do that. And this back. Okay, so this is our 2x squared minus 3x function that we're looking at here. Now, you'll see that indeed 2 is a point that is on this function. And I think I'm going to have to let my dog out of the office. So hold on just a second. All right, come on, girl. Let's go. All right, she will probably want to come back in about 5 minutes, but that's fine. So there is a point here, 2. Now, what does the f prime of 2 equals 5 means? It means that if we were to put a tangent line on here, and I'll try to maybe sketch what I think this tangent line, it's not letting me do that. But if you could imagine, if you did draw a tangent line, it would be a slope that's pretty steep and has a positive slope, and then it would nick the curve at that one point. All right, and in fact, let's do this. I'm actually going to draw the tangent line because I'm going to use point slope, as you'll see a little bit later on tonight. I'm going to show you how to use point slope. But I know that the point is 2, so I'm going to do y minus 2 is equal to 5 times x minus 2. There we go. So that right there, if you go to 2, that purple line right there is the tangent line that hits it at 2, and it has a slope of 5. And how do we know it has a slope of 5? Well, let's test it out right here. So you can see this passes through. It looks like 0.5, negative 5.5. So if we go up 1, 2, 3, 4, 5, and we go over 1, you'll see that it does indeed have a slope of 5. So I'm showing this to you to show you that the derivative will give you the slope of the tangent line that will hit the curve at a particular x value. At x equals 2, the slope of the tangent line is the number 5. That's what we saw. So let's go back. Let's go back here. So that is why we use derivatives. They allow us to find slopes of tangent lines on our function. All right, so what I want to do is I'm going to do one more. So this one that we did here was polynomial. So pretty straightforward. You probably have done polynomial difference quotients in your pre-calculus class. If not, you probably should have. So this should not be the first time that you've gone through this algebraic process to evaluate the difference quotient. But I'm going to do one here now on a rational function, y equals 2 over x. And I'm going to do it x equals 3. Now, I am going to use this, right? F prime of x is what I'm trying to find. And it is going to be the limit as h goes to 0 of f of x plus h minus f of x. All right, all over h. And again, if you are joining me live, please post a note in the comment section so I know that you're here. And if you have any questions, put those in chat, or you can shoot me an email. Right now, so what I'm going to do is I am going to evaluate this limit by finding f of x plus h. Well, that would be 2 over x plus h minus f of x, which is 2 over x. And that is all over h. Now, in order for me to evaluate this, I do want to combine these into one fraction. So I will do that. The common denominator here is going to be x times x plus h, right? So the common denominator will be the product of those two, x times x plus h. This function here, I would be multiplying it by x over x, and this one would be x plus h over x plus h. All right, that's just how I get a common denominator with rational functions. So this would end up being 2x, then there's a minus sign, and this would be 2 times x plus h. Okay, and we got to squeeze the limit in here, right? I don't get rid of my limit until I do direct substitution. So I'm taking still the limit as h goes to 0 of this. Let's simplify that. So the limit as h goes to 0, up here it's 2x minus 2x minus 2h all over x times x plus h. And notice over here, I left off my all over h. Okay, so that's a complex fraction that I'm working with. So I've got that, and that's all over h. Let's continue simplifying this. Now, if you're good at algebra, you can skip some of the details that I'm doing here and maybe combine 2 steps into one. But this ends up being negative 2h, right? Because the 2x and 2x cancel. So I have a negative 2h all over x times x plus h. And then that whole thing is over h. Well, if I do a fraction division, I would, and again, I'm going to show this in all of its detail here, because I don't want to lose anybody, but you could combine some steps here. But I'm going to write this as negative 2h over x times x plus h, and then I'm going to multiply by the reciprocal right here, right? To divide by h right here is to multiply by its reciprocal, 1 over h. So you can see what happens is those h's are going to cancel, and now I can take the limit as h goes to 0. And so this is going to end up being a negative 2x times x, or negative 2 over x squared. And that is it. Okay. Now, let's see where we want to go from here. Let's see. So what I did here, I think we can, so we'll stop it right there on that one. So that's my derivative function. But now look what it says here. It says find the slope of the tangent line to the hyperbola y equals 2 over x at x equals 3. So this thing right here that I found, that function, is the f prime of x. So if I want to know the slope of that tangent line, I would find f prime of 3, which would be negative 2 over 3 squared, or negative 2/9. That's the slope. When x is equal to 3 on that function, at the point of tangency, that slope will be a negative 2/9. All right. You can put that on Desmos and see if that makes sense. But now let me go over here to the next thing that I want to do. I'm going to move this guy out of the way. This up here. And I want to look at this problem. Suppose I have a function y equals the square root of x, and I want to find the equation of the tangent line to this function when x equals 9, and I want to use that to estimate the square root of 9.1. So I'm going to use this as a chance to show you how to find equations of tangent lines, right? And I'm going to start off by finding the derivative of this function. It's the first thing I'm going to do. So this is f of x. I am going to find f prime of x. And let's do that. So we are going to start again with our limit definition, right? The limit as h goes to 0 of f of x plus h minus f of x all over h. So let's do it. So we're going to say, okay, well, what is this? This would be f of x plus h would be the square root of x plus h minus the square root of x. And that would be all over h. Now, through direct substitution, that's 0 over 0. So what I'm going to use here is I'm going to multiply top and bottom by the conjugate of that radical portion up in the numerator. So I'm going to do this. I'm going to multiply this on top and bottom by the conjugate. We did this in Unit 1. It's one of our techniques for algebraically manipulating our expressions so I could find out what a limit is when I got 0 over 0 through direct substitution. So now what happens? Well, when I multiply these two conjugates, it's only the product of the first and last terms that is going to stick around, because the outer and inner products are going to cancel each other out. So this ends up being x plus h when I take root x plus h times root x plus h. And then this is going to be a negative x right here. Okay. And then down here, I've got h times root x plus h plus square root of x. So I'm just writing that as a product. I'm not going to distribute that to h. I am just writing this as a product. All right, well, what happens here? This does simplify because up on the top, the x minus x is 0. And this just leaves me with an h. And down here, I have an h. And I have a square root of x plus h plus root x. Well, lucky for us, those h's are going to cancel, leaving me, of course, a factor of 1 on the top. But now I can use direct substitution, because if I stick 0 in for h, I get now an answer. So I'll drop my limit because I'm doing direct substitution. I'm going to get a 1 on the top. I'm going to have a root x plus root x, which combining those together is 1 over 2 root x. And that is my f prime of x. When I take an f of x and I run it through that limit, at the end, after I've simplified and done direct substitution for 0 into h, that is my derivative function. Now, what I'm going to do next is, I think what I want to do is I want to go back to Desmos, and I want to graph the square root of x, which is what I am going to do. So let's do that. So this will be y equals square root x. All right. Let's go back. Let's see here. Yeah. So let me share this screen back and bring it back. There we go. There it is. So that is definitely y equals is equal to the square root of x. Let's see if I can get this pen to work. No. Now, what I'm going to do is I am going to come out here to 3. I think that's where we wanted to work this. At x equals 9, actually. So we want to look at this when x is equal to 9. Now, one of the things that I want to do here is, let's see, when we consider x equals 9 on this function, that would mean that f of 9 is the square root of 9, which is 3. Now, what does that mean? That means that there is a point, 9, 3, right, is on f of x. Okay, but I also want to calculate f prime of 9, because that tells me something about what's happening at x equals 9 on this function, f of x equals square root of x. It tells me what is the slope of the tangent line. So here's my derivative function. So f prime of 9 is 1 over 2 times the square root of 9, which is 1/6. Now, if we go back to Desmos here, and I show you this, if we come out here to 9, way out here to x equals 9, no surprise, there is the point that we knew was there, 9, 3. It's right there. Now you can see that if you were to draw a tangent line right there, it would have positive slope, but it would be not steep at all. And in fact, we know that that is a slope of 1/6 if I were to draw a tangent line that nicks the curve here at 9,3. Now, what's the significance of that? I'm going to show you. So this means that I have everything that I need to write the equation of the tangent line, because I'm going to use point slope. And in AP Calculus, we use point slope all the time. We are not always using slope intercept. I know through your algebra classes, you were taught y equals mx plus b. That is the way we write linear equations. But really, it's not the most useful form when you're trying to generate an equation of a line, because you need the slope, m, but then you need a specific point that's on the line, which would be the one on the y-axis. Well, with point slope, though, you need the slope, but you can use any point that's on the line. And this is point slope, right? So m is the slope right here, but my x1, y1, as you well know, as you learned in your algebra classes, that's any point that is on the line of interest, any point. So for us, we have a point that we're interested in, 9,3, and we know the slope at that point, which is 1/6. Okay, so this is called, right, or I would call it is called the point of tangency. I'll abbreviate that POT, the point of tangency. This is the slope of the tangent line, SOT we'll call it. And what I can do then is say, well, at that function, I now could write the equation of the tangent line, because I'm going to use point slope and stick in 9 for x1 and 3 for y1, and 1/6 is going to be my m, my slope. And so it looks like this. Y minus 3 is equal to 1/6 times x minus 9. I'm not even going to bother to put it in slope intercept. Now, I am going to move that -3 to the other side and leave it with y on the left side. So I'm going to write this as 1/6 times x minus 9 plus 3. Now, I'm going to go back to Desmos, and we're going to graph the equation of that line and see if indeed it looks like we have nailed it. So I'm going to turn this, I'm going to zoom out a bit here, okay? So you can get a better view of this. And I'm going to actually change this this y-axis scale, because I don't like that. So I'm going to go from -1 to about 6. And let's change the x-axis scale from -1 out to about 12. Okay, so this gives us a much better view of what we're looking at. So there we go. So there's the function in purple. And then here's the equation of the line that we just came up with, because I knew the slope of the tangent line at x equals 9, and I knew the point of tangency. And if we come out here to 9, Desmos knows that I'm probably interested in that point, so it allows it to stick right there. And you can see that that is the tangent line right there. So that's the, and now let me tie this back to what we talked about back in Unit 1. The slope of that line is the instantaneous rate of change of the function at x equals 9. That's what the slope of the tangent line represents. It represents instantaneous rate of change. The slope of a secant line is average rate of change over that interval. But when we have found a tangent line slope, that gives us the instantaneous rate of change of the function at that one particular point. I don't need 2 points. All right, so that is that. And that is the equation of that line. And you can see that it indeed looks like a tangent line. Now, one thing that I always show my students is that functions that are nonlinear, like this f of x equals square root of x, When you zoom in on a very small delta x, they don't look linear anymore. So if we come out here to this point of tangency and zoom in on it, you can see that you cannot even differentiate between the curve itself, the square root of x, and the tangent line, which is a straight line. They look to be almost the same. You see that there's, and here's the, just as a reminder, that's the point of tangency right there. So you can't even distinguish between the tangent line and the curve itself. But I'm looking over a very small interval if you look at my axis down here. But you can see some separation start to occur the further I get away from the point of tangency. But here's the thing. One of the uses that we have for tangent lines are they allow us to make approximations for y values of the function when I'm really close to the point of tangency. And so that's what I want to do now. I want to go ahead and use this tangent line to make an approximation for the square root of 9.1. So let me show you what I mean. So now that I've got this equation for my tangent line, right? This right here. Let's recap here what this thing means. That is the equation of the tangent line to the function f of x equals square root of x at a particular point 9, 3. So what I can do is if I want to estimate what the y value would be for 9.1, and that was I think our original question. Yeah. Use that tangent line equation to estimate the square root of 9.1. I'm going to do that by plugging in x equals 9.1 into this function. 1/6 times 9.1 minus 9 plus 3. Okay, that's 0.1. So this is 1/6 times 0.1 plus 3. All right. This is, let's call this 0.1 over 6 plus 3. Right, 0.1 times 0.1 over 1 times 1 over 6 would be 0.1. Let's call this 1 over 60, multiplying top and bottom by 10, plus 3. Wouldn't that be 181 divided by 60? I believe it would be. If I got a common denominator, that'd be 180 over 60 plus 1 over 60 would give me 181 over 60. All right, now I'm going to get the TI-84 out and see what that is approximately. So according to the TI-84, 181 divided by 60 is about 3.01. I'm not going to write it down. You can see it there on the calculator, 3.01666. Now, let's take the square root as a decimal of 9.1 and see how close our estimate is. Pretty close. It's accurate out to 4 decimal places. Now, why is that so accurate? Well, it's because I picked a point that's really close to the point of tangency, and that point being 9.1. Point of tangency is at x equals 9. And as you can see, the tangent line and the curve itself are like, you can't hardly distinguish them from one another on that Desmos graph. Now, the further that I go away from x equals 9, the less accurate my estimates will be. But we're going to use tangent lines as what we call linear approximations. Linear approximations. Now, as an electrical engineer, when I was in school, we used linear approximations, right? Because we worked with curves. One example is curves that demonstrate current versus voltage for a diode. It's a very it's an exponential curve, but usually with a lot of electronic devices, you're using them over a very small range of voltage. And so if all you're taking is a small slice of a curve, then basically the curve is linear over a very small range of values of x. And we even see that on this function, right? You can take any piece of this function, and when you zoom in on it, it doesn't look curved anymore, even a place that is like most curved here. So if you take a look at this point 1, 1, if you zoom in enough, it doesn't look to be curved over a small range of x's. So if I go to 1, 1, and I get the equation of a tangent line, I could use that to make approximations for the y values of this function, as long as my x values are really close to the number 1. And the closer they are to 1, the better the approximation is going to be. Now you may say, why not just use the function? Why use an approximation? That's a fair question. In the case of the functions that we would be using in that would represent the current voltage relationship for a diode, those are very complicated expressions, very complicated exponential expressions. So it's much easier just to use some sort of linear approximation to come up with the rough values for current for a given voltage. But anyway, so we use linear approximations to simplify our calculations rather than using the original function. Again, so long as we're picking x values that are close to the point of tangency. So I hope that helps. Hope that helps you see the use of just one use of a derivative, and that is to come up with equations of tangent lines, for which we could then come up with the once we have that tangent line equation, we could use it to make approximations of the function for values of x close to the point of tangency. All right, now I've got just a few more minutes, and I think I want to cover one more topic. Now, this is a topic I did not cover last week in class, but we most certainly will be getting to it this week. And that is, I want to go back up to this figure up here, and I want to show you that there is another form for the limit definition of a derivative. So this is the one that I developed from this picture right here. But the one that I want to develop now is another one here. F prime of a is equal to the limit as x goes to a, f of x minus fa, or x of minus a. So that is another, again, definition of a derivative. Now, this is one that's good to use if we're trying to find the value of the derivative at a specific x value. Notice that this one, what this does is it gives me a slope function. This allows me to get an actual function of x that returns slopes at values of x on the function. This would be one where I have a specific x value in mind at which I want the derivative. So let me just show you kind of how this would develop on here. If we rename some of this here, I'm going to rename, I will call this x over here. And this is a. This is the point at which I would like to know the slope of a tangent line. So I'm going to call that no longer a plus h. I'm not using this distance anymore like this. This y value now is f of a. This y value, since this is now called x, is f of x. Okay, and I'm going to erase this right here. Now I'm going to write the equation for that secant line, for the slope of that secant line. Well, in the top I have f of x minus f of a. That's the difference between my two y values. And then down here I have x minus a. But now if I want the point here to move down and get infinitely close to this point to convert that secant line into a tangent line, then I'm going to let x approach a. So I'm going to pull this x towards the a and let it approach a. So basically f prime of a would be the limit. I'm just rewriting what I have there. The limit as x approaches a of f of x minus f of a all over x minus a, like that. Now, when could I use that? Well, let me show you an example. So let's take this down here. What I'm going to do is I'm going to use that same function that we were just working with, which was y is equal to the square root of x. And I want to know the slope of the tangent line. And let's pick a different value. Let's say that it's x equals 16. Okay. So what I'm going to do is say, all right, well, so f prime of 16 is equal to the limit as x approaches a of, well, what does the formula tell us? Right. It is telling us right here. Let's bring that down. I don't think I pasted it. So let's copy this down. So we can see that. All right. F of x. So we're going to do f of x minus f of a. So I'm going to put f of 16 right there, all over x minus a, which is 16, because our a value here is 16. So it looks like that. So my a value that I'm interested in knowing the slope of the tangent line is 16. So a is 16, 16, 16. So let's evaluate this. So the limit is x. Now, direct substitution, you can see it's 0 over 0. So it doesn't mean that the limit doesn't exist. It just means we don't know what it is. So we've got more work to do. So we say the limit as x goes to 16. This is f of x, which is the square root of x. But I do have a number for f of 16. That's going to be a 4. Okay. And then this is going to be x minus 16. Still, you can see I still have 0 over 0 through direct substitution. But what am I going to do here to evaluate this? Well, I'm going to multiply by the conjugate. Square root of x plus 4 over the square root of x plus 4. And see what happens. I'm multiplying these two conjugates, which means I'm going to have x minus 16. Down here, I will have x minus 16 times the square root of x plus 4. Well, look what happens, right? From that conjugate product right there, I have x minus 16 canceling that x minus 16, leaving me a factor of 1 on the top. I can plug 16 in now, and I get 1 over the square root of 16 plus 4, or 1 over 8. Now, what would the equation of the tangent line be? We have enough information because my point of tangency is 16, comma 4, right? Because if I stick 16 into my original function, I get a y value of 4. And the slope of the tangent line, we just calculated as 1/8. If I throw both of those values into point slope, I get y minus 4 is equal to 1/8 times x minus 16. Okay, let's move the minus 4 over, and it gives us a function that looks like that. I'm going to go over to Desmos, and we are going to graph that and see if we got it right. Here. All right, so we still got our square root of x function there. Now, what we now is 1 over 8, and then times x minus 16, and plus 4. Nope, we need to go over to here. X plus 4. All right, we're going to zoom way out on this guy. There is our, hopefully our tangent line. So we're zooming way out, coming way over here to 16. And did it find it? Are we on it? Are we on it? Yeah. So there is the, that's the point of tangency 16.4. And sure enough, you can see that that is the tangent line equation. All right. So the rate of change of that function at x equals 16 is 1/8, because that is the slope of the tangent line. Okay, I think we're going to leave it there for tonight. So again, if you found some value in this video and you're watching on the replay and you made it all the way here to the end, hit like and subscribe so you get notified on my future live streams. And if you have any questions, post them in the comment section. Let me know that you watched it. I appreciate you coming. Next week, we'll be doing more things on derivatives, and we'll be meeting here at 8 o'clock next Sunday night, as we do every night. Hope you all have a good night and a great week at school. Thanks for coming. Talk to you soon.